Let us look at the reversible reaction of evaporation and condensation in a closed system. A reversible reaction can be likened to the situation in and out of, and movement into and out of, a shop. At any one moment, there are a certain number of people inside the shop and a certain number of people outside the shop. During any period of time, a certain number of people enter the shop and a certain number of people exit the shop. In other words, there is an entering rate and an exiting rate. Imagine that we place some water into a container which we then seal. What would the level of the liquid water be at various moments after sealing the container? The humidity in the container refers to the amount of water vapor in the air within the sealed container. What would the humidity be like at various moments after sealing the container? Also, compare the evaporation and condensation rates at various times. Assume that temperature remains constant. Copy this table and then fill it in, pausing the video until you've done this. We could think of this situation like the shop analogy. Just after the shop opens, there aren't yet many people inside the shop. Most are still outside. Few are inside. And this would mean that the number of people in the shop would increase and the number of people outside the shop decrease, because the rate of entering the shop would probably be higher than the rate of leaving the shop would be. More people would enter than leave, increasing the number inside the shop to this state and decreasing the number of people outside the shop to that state. However, as the shop gets fuller and so more squashed, more people would want to leave and fewer would want to enter. Thus, that would decrease the entering rate and increase the exiting rate until the two rates are equal to one another. At that moment, just as many people enter as leave the shop in a certain time, and that keeps the number of people in the shop constant, even though who exactly the particular people are that are in the shop changes as time passes. Now, you must just notice that this analogy is not perfectly synonymous. It's not exactly the same as that of a reversible reaction. In other words, it doesn't correspond perfectly. And that's because people, unlike molecules, do not move around randomly. Instead, they have their own free will, of course. But in a somewhat similar way, just after the liquid water is sealed inside the container, there is much liquid water, but little gaseous water. The rate of evaporation is high, and the rate of condensation is low. Why is it like that? The rate of evaporation is high because of the low pressure exerted by the few water molecules on the water surface. And why is the rate of condensation low? Because there aren't many water molecules in the vapor form in the air. And so there aren't many that can collide, can bump against one another and stay together and therefore condense. But because the evaporation rate is high and it's higher than the condensation rate, that causes the amount of liquid water to decrease over time and the amount of humidity of vapor in the air to increase over time. And what does that do? Well, the increase in humidity causes a greater pressure to be exerted by those water vapor molecules. And so that resists evaporation, causing the evaporation rate to drop. Meanwhile, of course, because now you have a higher humidity, you've got more water vapor particles in the air, and so the water vapor molecules are more likely to collide with one another and so condense. So the condensation rate has been increased. This happens until the two rates, condensation and evaporation, are the same rates as one another. And once that happens, the amount of water stops changing, the level of water stops changing. Also, the humidity stops changing. It remains constant. However, which particular water molecules are in each phase at any moment does change over time, since water molecules do continue to evaporate and condense. It's just that the rates of evaporation condensation are equal, and we call this dynamic equilibrium. Dynamic means moving. This means that although the reactants continue changing into products and the products continue changing into reactants, since this is happening at the same rate as one another, the amount of each isn't changing as time passes. Draw a graph with two plot lines, one for the change in concentration of products as time passes, and one for the change in concentration of reactants as time passes. It is actually not really correct to speak of concentration when we're speaking about water, because water liquid cannot change in concentration. A liquid's concentration is fixed. It doesn't change. But because evaporation of water is a familiar situation, that's why I've chosen to use it to introduce the concepts related to equilibrium. Pause the video until you've drawn this graph yourself. In this case, the concentration of reactants corresponds to the amount of liquid water, and the concentration of products to the amount of water vapor. The concentration of reactants in the closed system decreases with time until equilibrium has been reached, after which the concentration of reactants remains constant over time, shown by the zero gradient of the graph. The concentration of products in this closed system increases over time until equilibrium has been reached, after which the concentration of products remains constant over time. At equilibrium, are the amounts of reactants and products equal? To help you think about this, consider the shop analogy. Equilibrium is reached when the number of people entering the shop in a certain time is equal to the number of people exiting the shop in that same time. Does that mean that the number of people in the shop must equal the number of people outside of the shop? No, not necessarily. It could be so, but it doesn't have to be so. To help us to think about this, we need to think of a situation which is a bit like a closed system. Maybe a mall containing a certain number of people who can't leave the mall. The rates of entry might equal the rate of exit for one shop in the mall. But although the number of people inside and outside the shop won't change as time passes, this doesn't tell us anything about the number of people in the shop compared to how many are outside. There could be many inside and few outside. There could be few inside, many outside, and yet the rates of entry and exit be the same as one another. That has nothing to do with the ratio of people inside and outside. Similarly, at equilibrium, although the amounts of reactants and products each don't change over time, their amounts are not necessarily equal to one another.